In this week, we will discuss the formation control problem. Formation control problem can be characterized as controlling agent to form a specific geometric patterns. Formation control has been used in many different applications, such as military and entertainment. Also, we can find formations in biological systems, such as the V shape employed by geese and other large migratory birds. In this way, it is thought that the geese can reduce the drag force or the air resistance, and also it can increase their visibility. So basically, we want to show you how we can extend the agreement, the consensus algorithm we learned so far, to extend to solve the formation control problem. So for formation control problem, we want to control the agents to moving agents in a way they satisfy a particular shape or relative state. For example, in this case, we have 6 agents. Then the 6 agents can be separated into 2 groups, and each group can form a triangular shape. And the 2 groups can join together to form another shape. Then the formation can be changed to form another shape. So information control problem can be defined by a shape or relative state, as well as an assignment problem. So the first component is like we want to control the agents, so the agents can form a different shape. A second component, like assignment component, is like we want to assign role of each agent in a formation. So we will start by specifying the formation. Then we will study the notion of graph rigidity. To specify the shapes, we use the interagent distance. We can define a site D. The D used to define the shape of the formations. So in the site, we define Dij as the distance between agent I and agent J. Then we know the Dij is always greater than 0 if I and J are different. So we assume that 2 agents are not at the same locations. We know Dij is always the same with Dji. This means the distance between I and J is same with distance between J and I. So we define the distance for all agents in the network. So I is from 1 to n, and J is also from 1 to n. For I, it's not same with J. Then we assume that this formation is feasible. By feasible, we mean that we can find some point, C1, C2, and Cn, so that Ci minus Cj, the distance is dij for I from 1 to n, j from 1 to n, I is not same with j. Then also we need to specify in what domain we can find the feasible formations. For example, if we pick the Q as 2, it means we're in a planar case. So if P is 3, we're in a 3D case. So the feasibility may depends on the domain you're talking about. In some cases, it may be feasible in 3D, but it's not feasible in 2D. Next, I will show you an example of a feasible formation and an infeasible formation. For example, we can pick the D site is used to define the shape. We have 3 agents. Agent 1, agent 1, agent 2, and agent 3. Then we specify the distance between agent 1 and agent 2 is 1. The distance between agent 2 and agent 3 is 1. The distance between agent 1 and agent 3 is 1. Then we can find the, let's discuss this problem in P is 2 in planar case. So in this case, we can find scalars, because C can make this formation feasible. Then we can establish the coordinate. Then we can pick agent 2 as a location, pick C2 as 0, 0. Then we can pick C3 as 1 and 0. Because the distance between 2 and 3, they're 1. Now we can pick, so this is half. And this is, yeah, then the agent 1, we can pick the C1 as half square root of 3 over 2. So we also know that if we can find C in this way, then we can move this shape along the coordinate by keeping the distance. So it will still satisfy this coordinate. For example, maybe we can shift the 2, 0, 0 by 1, 0. Yeah. So we can also rotate. For example, we by take agent 2 as the origin, then rotate agent 1 and agent 3, keep the distance. So it will still satisfy this side constraint. The shape is not changed. We also discuss in this case is infeasible case, in P is 2, in planar case. Let's specify agent 2 still. Let's say because 2 is 0 and 0. The distance between 2 and 1, 2 and 3 is 1. Then we can pick C3 as 1, 0. So the distance between 2 and 3 is 1. The distance between 1 and 2 is also 1. Then there are many different choices, okay? So agent 1 can rotate by taking agent 2 as the center and with 1 as a radius, draw a circle, okay? So agent 1 could be anywhere in the circle. But no matter where agent 1 is, the distance between agent 3 and agent 1 cannot be 3. Why is this case? Is based on the triangular inequality theorem. The triangular inequality theorem states that the sum of the lengths of any two sets must be greater than or equal to the lengths of the remaining set. So this two set, the sum is 2. So it's not possible for 2 is greater than 3. So for this specification, and it is infeasible, cannot form any shape to satisfy this formation. Let's also define the scale invariant formation. For scale invariant formation, we have this set of D to specify the interagent distance. Then we say this formation is scale invariant if there be any positive alpha is greater than 0. Then we say this new set S is also feasible. Then it's scale invariant formation. So scale invariant formation can be applied in cases the environment is changing. For example, in this case, now the agent satisfies the formation specification by the set D. But when the agent is moving this way, this formation set is always satisfied. Okay, the D is always satisfied because the distances are kept constant. In moving this way, because this passage is narrow, it's not possible for agents to maintain the original formation D to pass through the narrow passage. So in this way, we can contract or by scaling down the formation to form a smaller size of triangular to pass through the narrow passage. And after they pass through the narrow passage, they can return to their original formation. So also know that the alpha could be greater than 0, less than 1. Then we contract the triangular. If alpha is greater than 1, we expanded the formations. So later on, we will know we can also define different formations. For example, by switching the formations in this case, when the agents are trying to pass through a narrow pathway, not by scaling, because in most common type of formation specification, the scaling is not allowed. So the formation specification is exactly given in terms of interagent agents, but by scaling, the interagent distance are changed. As we mentioned that if the agent can form some shapes, for example, square shape, we have agent 1, 2, 3, and 4. This is the coordinate. But if the agent rotate, let's say the distance is 1. If the distance rotate, let's say we have 1, 3 this way, 2 this way, 4 this way, we will see the distance specification is still satisfied. So let's see will be the any realization of the specification of D, but X will be the prediction of the agent. We know we can move this formation by rotating and or moving to different locations, but the specification is still satisfied because the distance are kept constant. So the distance difference between agent I and agent J is the same with Dij without changing anything. Now, if we want to put another constraint, okay, let's say the formation is only allowed to be translational invariant. Let's say we only allow the agent to move from one location to another location by moving to the right or to the up or by combination of right and up or down and left, not rotational motion. So rotational motion is not allowed. Then we can specify this by translational invariant. By translational invariant, we mean if we have a specification, okay, we want to specify the interagent distance. We can find some realization, C1 and Cn. So the only motion allowed is by the location of the agent xi will be Ci plus tau. Tau could be any vector in Rp. So the same tau for all agents. Now you see that if I define Ci as xi minus tau, then eventually let's say in this way, okay? If I define xi minus Ci as a new variable yi, so eventually we want all the yi convert to tau. This is exactly the consensus problem. As we know, this tau is arbitrary. So as vi converts to tau, so xi will convert to Ci plus tau. So now we make the connection between the consensus problem and formation control problem. As we say, this is only the case for translational invariance case. It doesn't apply to this case because this case allows the formation to rotate. So if we only allow the formation to have translational movement, then the formation control problem is equivalent to the consensus problem.